Hello, everyone, everywhere in the world. So good morning, good afternoon, good evening. My name is Ahmed Atiyah. I'm the VP of OptiSystem at Optiwave System Incorporation. Today, we're gonna have a webinar entitled of Equipment Automation for PIC Characterization using OptiInstrument software. We have collaborators, Dr. Henning Helmers from, he is a deputy head of Department of Photovoltaic and concentrator at the Fraunhofer Institute in Germany, and Dr. Megan Petty. She's a postdoc researcher in solar energy and photovoltaic at University of Ottawa Sun Lab, and also Alex Ritchoff. He's a software engineer at Optiwave. The webinar today, we're going to give some overview about Optiwave, and then we're going to show the features and applications of OptiInstrument software. Then Dr. Henning, we're going to talk about the Photonic power converter chip design and functionality. Then Megan, she's going to talk about the equipment setup used to characterize the Photonic power converter chip at the University of Ottawa. Then Alex is going to show the scripts used to run an OptiInstrument, so software to test and characterize the Photonic power converter chip. And then we're going to open the floor for questions and answers. Optiwave is established in 1994 and located in Ottawa, Ontario, Canada. Optiwave developed different types of software packages used to design, simulate, and optimize photonic components, links, system, and networks. We offer at Optiwave a distinctive competitive advantage to users through shortening the product timeline introduction to market using simulation capabilities of the different software. Also improving the quality of the product, because you will be able to do simulations and conditions which you may not be able to do it under experimental simulation, experimental verification. And then also the software can enhance productivity and cost effectiveness. Optiwave product has been sold in over than 1,000 industry-leading corporates, universities, research, and governmental institutions over than 80 countries in the world. The products at Optiwave, we offer different packages. The first one is system-level packages, including OptiSystem software and OptiSpice software, which is an optoelectronics software package, can be used for designing photonic integrated circuits. The second category is the component-level package, which includes beam propagation method software, finite difference time domain software, mode solver software, as well as fiber and grating software design packages. The last one of the software we offer is the instrumentation level software, which mainly today's webinar is about. It's OptiInstrument and can be used for communication control, different equipments from different vendors in the single GUI. Now, if you are interested in downloading the different software packages from Optiwave, you can go to the website of Optiwave, and then under download 30 days evaluation, you can download any package of the software for 30 days free. You need to register in the on the website page, and then after that you will be able to download the software, and the software will be going under the program files of Optiwave software. As you can see here, this is the different packages on the C drive under program files and Optiwave software, where you can download it. And then after, for each software, you have the drivers, the documentation, and then you will be able to download examples for the different software. In this picture here, we show OptiInstrument software installed on a laptop, which, as I mentioned to you, can communicate with and control equipment from different vendors through TCP/IP, through the internet, or through a USB cable or serial cable, RS-232 or RS-4085, or GPIB. So all of these communication capabilities can be done through with the OptiInstrument software. This is the GUI look. It shows, as see here, there is different windows, and these windows, most of them are dockable, so you can move them around. And then it has all the functionalities. It has a Python editor, which is a very powerful tool you're gonna see used in this software. Now, I'm going to talk here about some applications and features of OptiInstrument software. As I mentioned, it can be communicating with the equipment in the same location or a different location remotely. You can set up parameters of the equipment. Then you should be able to automate the testing, the characterization, which we're going to demonstrate today in this webinar. And then you would be able to capture data, process the data, save, display single trace or multi-traces of this collected data. You can save the data in JSON file format, text format, CSV file, or any format you are interested in. We offer capability to process the raw data captured from the equipment, so the user can manipulate the data if he wants as required. And also we support execution of a single PIC visa or NI visa commands to build your sequence of commands to control the equipment. And also we have the custom Python file loading, which we're going to demonstrate today to control the equipment used for characterizing the Photonic integrated chip by University of Ottawa. Okay, OptiInstrument, once you download it, you will be able to have access to different examples we created from different vendors. From Expo, we have examples on the LTB8. We have examples on the CTB10 equipment. These two equipment from Expo, we have a webinar already recently with Expo, jointly done with Expo, and we showed how you can use the different cards to do testing and characterization. This would be also an essence for testing Photonic integrated circuits. There is examples on Rigol, on OSTEC, Keithley, Keysight equipment. Okay, and we are open to add up any equipment for any user or customer interested to control and communicate with. This is just quickly showing the cards, which is have examples on it. In the LTB8, there is a broadband source, there is an optical spectrum analyzer, power meter, transceiver characterization, so you can do BR testing and all this in a power Blazar card. There is a variable optical attenuator, CW lasers, OTDR, switches, tunable lasers. So these all cards are basics cards you can be using for testing Photonic integrated circuits. Also, we have the examples on the CTB10, which is for insertion loss, return loss, and PDL characterization. This is just quickly showing the setup we use to do the development of the script to control the different cards implemented in the LTB8. As you see here, there is a switch and OSA card and so on. This is the setup for the CTB10, just quickly to show it to you. There is a tunable laser, there is a different cards to place the detectors in them, and then you test the device under test in it. So here is a picture of the OSTEC laser, high power laser driver and temperature control equipment, which we going to be used exactly today to control the lasers which are used to test and characterize the photonic power converter chip, as you're going to show by Megan and Alex. This is the Keithley source meter used to collect the data for the IV curves, and then we communicate with it and then create graphs and process the data afterwards. Now I'm going to move the podium here to Dr. Henning Helmert, who is going to speak about the photonic power converter chip and design. So I'm going to stop sharing here. Henning, take over, please.
Okay. Okay, now how do okay, do you see my screen?
Yeah. Thank you.
And how do I get rid of this? So, okay. Yeah, hello everyone, and thanks so much for having me today. I'm happy to give you a quick introduction into 3-5 photovoltaic cells for photonic power transmission. And it's a very quick overview. So I'm happy to have a discussion later on if you have any questions on that. So, okay, very briefly, this is as mentioned. So my name is Henning Helmers, and I'm with the Fraunhofer Institute for Solar Energy Systems in Freiburg in Germany. And this work is actually supported by the German-Canadian binational project, which is called Air Power, with a AIIR, so that's Artificial Intelligence Infrared. Here and in Germany, it's funded by the Federal Ministry of Education and Research. And it aims at an application that we call Power by Light, which is also a business unit at the institute that I'm coordinating. So in principle, the idea here is shown in this slide. So basically what we want to do is to transmit photonic power or optical power and possibly also data to actually power an appliance, whatever that may be, on the right-hand side. So basically there's two different ways of doing that. On the left hand, you have the emitter here, which is a laser source. Principle could also be an LED, for example, that is either transmitted through an optical fiber, as shown here on the top left, or through free space. So in fact, wireless power transmission. On the right-hand side, the receiving end of this light beam, there is a photovoltaic cell, which is not a solar cell because it's not operating under solar light, but in principle, it's the same technology. But it's a device that we call the photonic power converter, which is now optimized for this very narrow band or even monochromatic light of the laser. And there's various kinds of applications for that, a few of them depicted on the right-hand side here, or the advantages that you have, because basically what you have is now a galvanic isolation between the two sides of your load, the left and the right-hand side, the receiving and the transmitter side is not connected. It's electrically anymore, and you can even have free space beaming. And there's a number of applications operating with that, a lot of them in sensing, Internet of Things, and etc. So that's really an enabling technology and emerging applications coming into play more and more. Quick dive into the semiconductor physics, if you will. So the photovoltaic light to electricity conversion is depicted here. Very briefly, on the right-hand side, you see a cartoon of the band gap, the main property of the semiconductor. For standard solar cells, this will be silicon. And on the left, you see the broadband spectrum that you have at like 1.5 air mass here on Earth, typical spectrum. And what we have here is like lots of high energy photons, low wavelengths. This is the UV guy here on the right in the cartoon. High energy excites an electron way into the conduction band, and it thermalizes down to the band edge, which is an energy loss. And there's also low energy photons like this infrared guy here, this tiny red guy, which have an energy that is not enough to excite the carrier into the conduction band, and thus energy is lost as transmission. And this thermalization and transmission loss is actually the major loss mechanism, fundamental loss mechanism for a solar cell. And now if we go for laser light and for this, like for example here for 1550 nanometer light, C-band, which we look into in this project, of course, in principle, at least, both of those two mechanisms can go down to maybe not zero, but like can be reduced very, very much. So we use 3.5 semiconductors, compound semiconductors, to build now absorber materials with the right band gap for these wavelengths. So of course now it can be any wavelengths, any laser you have, we can build basically now a perfect suitable photonic power converter with. Here on the left, you see the example part of the periodic table of elements, which I guess you're familiar with. And on the right-hand side, you see the band gaps of these materials. So points is binary crystals, and then the lines in between 2 points is ternary crystals, and we can even have quaternary or even more complex compound semiconductors. And by playing around with the composition, you see that we have basically access to all the common wavelengths that are in use today, from the visible even spanning into the near infrared. And this is something that we also did experimentally. So here's I brought you a spectral response curve of different devices. So this is actually measurements of devices that we have realized here at Fraunhofer ISE. I don't read through the material systems here, but you see similar behavior, always increasing spectral response. So how much current do we generate per incident power? And then it peaks somewhere. And this peak is not coincidentally, of course, now matching with like these typical laser wavelengths that we have on the market. So basically the message here is we have absorber materials that are suitable for all these lasers. And I would like to go through some example. One is the maybe most exciting one, which we published recently, a world record in photovoltaic power conversion efficiency, which is shown here. So this is a result that we achieved with a gallium arsenide-based device that we processed in a thin film technology. So on the left, you see a little schematic. We removed the substrate and we replaced it with an optical mirror that is at the same time an electric contact. And by that, we can kind of build a little cavity that we can make use of optical resonance and another effect that is called photon recycling that pushes the voltage. And I don't have the time to go into further detail, but there you find more information in this paper here if you're interested. And we achieved actually a world record in photovoltaic conversion efficiency of 68.9% with this technology. And I should say that the voltage, the open circuit voltage of this device is around 1 volt. You see that in the bottom here, VOC, that's the open circuit voltage of the device. So now if we go to more telecom wavelengths in the O band, around 1300 nanometers, we have, I brought you some measurements of a recent publication of Megan Beattie, who will speak right after me today, of devices that we fabricated at ISE, which are made of this quaternary material, indium gallium arsenide phosphide. And this is now with a band gap of around 0.9 electron volts. And there is a quantity which is known as the band gap voltage offset. Again, I don't go into further depths here into the semiconductor physics, but basically with a lower band gap, we also have a lower voltage. And you see that with the IV curves shown here in the center picture that have open circuit voltages at zero current around, let's say, 0.7-ish, decreasing output voltage. And still, we had achieved efficiency here, maximum efficiency of almost 53%, which is also quite an impressive result. And now in this air power project, we go for 1550 nanometers C-band light, and we use another material, which is indium gallium arsenide for our cells that is ground lattice matched on indium phosphide substrates. A sketch of the structure is shown here on the left-hand side, which is the absorber cell cladded by higher band gap barrier layers. And the indium gallium arsenide has a band gap of 0.74 electron volts. Again, because of this, like what is called the WOC, the band gap voltage offset, which is kind of a fundamental reduction of the band gap for the voltage that you can have. Again, the voltage is even lower and even below 0.6, 0.5-ish volts, which is typically not enough to actually run electronics on that. So for this power by light application, we need to do something about that. And what we did in the project so far, or one of the steps we take, is we follow a approach which is called the multi-junction approach. That's a very old idea of stacking individual cells on top of each other in a monolithic stack. So we grow that by metal organic vapor phase epitaxy, and we can grow this entire stack of, in this case, 10 subcells in one growth, and we interconnect them in series by tunnel junctions, so that in the end the entire chip is not a single cell, but now already a kind of a module, if you will, a series connection of 10 individual cells. And of course, in a series connection now we basically we add up the voltages of all the individual cells. So at the same current, the voltages add up, so that in the end, we multiply the output voltage by the number of junctions. So this is the way we can increase the output voltage. And so for this 10 junction cell, which we have developed, I show you very first measurements under laser light that were measured by Megan. in Ottawa under this 1550 nanometer laser. And you see that here this very nicely holds. So for roughly the same current densities in amps per square centimeter, we get now voltage which more or less exactly multiply the output voltage by 10. And with that, I am through with my quick introduction into the devices, and we'll hand over, I think, to Megan to show how actually those measurements are done and what is so interesting about it. Thank you.
Thanks, Henning, very much, very interesting presentation. Thank you. Now we're gonna, I think, move to the podium to Megan, and she's gonna talk about the photonic power converter characterization setup at University of Ottawa. So go ahead, please, Megan.
All right, thanks very much for the introduction. So you can see my screen and everything. We're good. Okay, perfect. So again, my name is Megan Beattie. I'm a postdoctoral fellow at the University of Ottawa in the Sun Lab Solar Research Group. And I'm going to talk to you a little bit about the photonic power converter testing station that we've built here at the University of Ottawa. So essentially, we had an older version of the system on which we did some measurements that Henning has already showed you, and I'll talk a little bit about that. And we've recently made some improvements with, including adding in the OptiInstrument capabilities from Optiwave. So the general layout of the system, we have our laser light coupled into an optical fiber. The output from the fiber is collimated. It can be filtered to reduce the intensity as needed. And then the light reflects off of a mirror and moves down through another lens that focuses the light onto the cell under test. So the cell itself is mounted on a temperature-controlled stage, and we can adjust the profile of the incident light, so the size of this spot and the intensity profile, by adjusting the position of this lens so that we're effectively changing the lens to sample distance, which adjusts that spot size. So Henning already showed these results, so I'll just go over this quickly, but these are some measurements that we did that we recently published in the Journal of Photovoltaics using the previous iteration of the system before we added the OptiInstrument capabilities and other improvements. But you can see some of the capabilities here where we were able to measure the efficiency as a function of the incident irradiance from our laser at a variety of different incident beam profiles. So very non-uniform profiles and profiles that are a little flatter. And we found that these particular chips that were fabricated at Fraunhofer for 1310 nanometer illumination, they tolerated non-uniform illumination at the lower intensities, and at higher intensities, we did start to see that efficiency dropping off. Some of that could probably be mitigated with different thermal management strategies and different designs. But overall, the chips performed very well, and we did have this 52.8% efficiency, which is the highest efficiency recorded to date for a 1310 nanometer photonic power converter. So if you're interested in learning more about these results, they are published in the Journal of Photovoltaics. Myself and Henning as the first two authors. Moving on to the station that we have now. So this is we have two infrared fiber coupled lasers. This is our 1310 nanometer laser back here that was used for those measurements I just showed you. We've also added a new 1550 nanometer laser. This is a 15-watt laser. And it operates 1550 nanometers, so this is in the telecom C-band. So looking at potential applications for power over fiber or power through free space at that wavelength. So those fibers are coupled into this light box. So the box itself is going to contain all of the light to keep the system safe. And up above, we have the electronics. So we have a Keithley 2420 source meter, which is making electrical connection to the cells under test. And we also have an OS Tech laser diode controller. This is driving those lasers that we showed. So we have this one and we have another one that's behind that you can't see, but one for each laser. And both of these devices can be controlled using the OptiInstrument software. So this is a vertical or a top view of the system. So we have the fiber light coming in here. There's the fiber input. The light travels to this collimating lens and then passes through this opening. So of course, these two segments of the box can close. And we can manually slide this beam block along a track here. So it could block the light to fully contain the laser light within this portion of the box, allowing us to open up the other half as needed. Once we move into the other half, you can see here that we have, again, the fiber input, collimating lens, and beam block. We have filters here that allow us to attenuate the beam as needed, a mirror, and then the focusing lens. And the cell under test is mounted on the stage down here. So we'll get a better look at that. So again, the light's coming through the focusing lens and down to the cell under test. And a temperature control check here. This image is just showing, I've turned on, both of our lasers have a red pointer light, so you can align the beam without using the invisible infrared light. So the pointer light is turned on here, and you can see some of the light passing through down to the sample check. We make electrical contact to the samples using micropositioner probes, as you can see here. And these are some of the measurements we can do. So using OptiInstrument to automate the testing system, we can measure current voltage curves. So Henning showed you some of our most recent results there. Essentially, the current voltage curve is just current as a function of voltage, and what's labeled MPP here, this is the maximum power point. So that's where the largest power is produced. That's where we want to operate the device. But we also look at other parameters, including the ISC, which is the short circuit current, VOC, which is open circuit current, and some other parameters. So we can measure these IV curves either in the dark or under laser illumination. We can also monitor the current at a fixed voltage. So for example, we could fix the voltage to 0, which is the short circuit condition, and monitor the short circuit current over time. We can do the same thing at voltage, so measuring the open circuit voltage and monitoring over time. This might allow us to see if the chip itself is heating up. You would see a shift in the VOC. So this is something that we can measure. Finally, we can do simultaneous illumination with both of our lasers at the same time, so both 1310 and 1550 nanometer light, which would allow us to do some more advanced characterization. So that's a general overview of the measurement system, and I'll at this point pass it off to a demo so you can see how this works.
Thank you, Megan. So yeah, I'm gonna right now show a demo for running the scripts in OptiInstrument software. So the scripts which developed by Optiwave in collaboration with University of Ottawa with Megan, and Alex is going to show how to manipulate the scripts and how to collect the data and run it through OptiInstrument software. So I'm going to now move into the video here. We record the video for it.
Hello. In this video, I'll be showing you how to do a photonic power converter chip automated characterization using OptiInstrument. What is OptiInstrument? OptiInstrument is a software that specializes in automating tests and sequences for scientific equipment. It works by creating instrument objects that can be assigned programmatical commands provided by the vendor of the equipment. Let me begin by opening the software. The first course of action that I can do is scan for connected instruments. Instruments that are connected to the computer via TCP/IP, USB, RS-232, and GPIB will appear in the Instruments tab. If the instrument does not appear, I can always enter the address and port. Now I can begin to assign commands and build my sequence. Standard commands for programmable instruments, or better known as SCIPI, can be assigned to the instrument of my choice. I can query or write the command in the single command panel and see the result it gives me. If I'm satisfied with the result, I can add it to my overall sequence of commands. Helper and custom functions can be used in combination with the Skippy commands to create more sophisticated and flexible tests. I can add if statements, loops, sleep timers, prints, variables, or just general statements. For instance, if I wanted to run the same command 5 times, I would add a loop with 5 iterations. I can use these controls here to move the commands around. 5. Now if I were to run the test, I would press my run all sequence of commands, and I'd have the same command outputted 5 times. If I'm satisfied with my results and the test I've written, I can actually export the test and save it for another time. Then when I wish to continue working on my test, I can reopen it, drag it back in, and expand upon it. For this webinar, I'll open and talk about some of the sequences related to the photonic power converter. The sequence here is the dark IV measurement. And while it may seem daunting at first glance, the sequences themselves are not too complicated. And as I showed earlier, you can always add one line at a time, run the sequence, and expand upon it that way. Something to mention before I begin explaining the sequence is that you can also write your own custom functions and load them in to be dragged in combination with the rest of the commands. So for example, I wrote this folder called OS Tech Test. And what it does is I have connect, disconnect, get value, write value, and export functions that are specifically tailored to the sequence that I want to run. And what I can do is I can actually drag these commands into my sequence and use them that way along with everything else I just mentioned. The first part of the sequence are my user-defined inputs. My user-defined inputs for the first part are variables that I want to export through this export custom function that I wrote down here. So I'm going to be exporting the sample name, the user, some notes that I want, and other variables that I can, of course, always add to this file. The next section that I'm defining are these Keithley settings. I'm setting up the source voltage, the min, the max, the step value, the current limit, and the NPL cycle, which is the speed at which the source meter queries values. The next part of my sequence is actually setting these Keithley settings onto the source meter themselves. So I'm going to set the function mode to voltage. I'm going to set the current protection level, and I'm going to set the voltage and current NPL cycle, which once again is the speed. And then I'm going to turn my output on. Once my output is on, I'm going to measure the current and the voltage between two values that I've assigned. In this case is the min and the max over, and then select how many points I want, which correlates with what kind of step size I want. If I have a higher number of points, there's going to be a lower step size. And this is done throughout 3 different loops, and then the values are going to be graphed and then saved using this custom export function that I defined earlier. As I press play, you'll begin to see the sequence unfold as I just described. First, the Keithley will reset itself, and after about 3 seconds, we'll then start to send the commands that I mentioned earlier. It'll set the mode to voltage, it'll set the current limit, and then it'll set the NPL cycle, both the current and the voltage. Then it'll begin executing those 3 loops that I mentioned, where it measures the current and the voltage between a min and a max and a fixed step size that I specified. As you may have noticed, there was about 700 points in one of the loops and a couple hundred other in the other 2. Therefore, I will fast forward a part of the sequence as it just collects the current and the voltage data. Once it is done sending Skippy commands to the device, it will then plot the data and save the results to the exported SCSV file that I specified in my custom function. As you can see, I have my dark IV curve, and all I had to do was press play on a pre-saved XML file that I created in OptiInstrument. And the advantage to this is that it saves time by not having to do each one of these loops individually and concatenating all the data to create my dark IV curve, when all I had to do was create this sequence that can do this for me anytime I wanted to. Seeing my dark IV curve and that I'm satisfied with it, I can now move on and do a light IV test. As you may notice, the script is going to be similar in many ways. First, I'm going to define these header inputs, which are variables that are going to go to my export file, such as sample source, sample name, user, laser wavelength, lens position, filter, notes, etc., and anything else that I'd want to add. I'm then going to have a section for my laser settings. Since I want to run a loop that's going to run 4 times, I'm going to set all the laser currents that I want in this list. So at 10 amps, 12, 14, and 16. Then I'm going to have my laser currents and move on to my Keithley settings. I want to have a start point, which is start in voltage, a stop in voltage, a step size, a current limit, and a speed of 0.1. Then I'm going to have Keithley settings that are going to kind of define the logic of my script. So I'm going to have this various step size, and I'm also going to have this little if condition here that's going to determine the direction of my sequence. If the stop is greater than the start, it will move forward. If the start is greater than the stop, it will move in a reverse direction. These functions here are going to control the high-powered laser. I'm going to set a temperature limit of 30 and a temperature target of 25. I'm also going to set the Keithley settings in a similar way that I did in the last script. I'm going to set my protection level, my NPL cycle, and then I can begin executing my sequence. I'm going to start with this list here, and as I mentioned earlier, there are 4 currents on my list, so it's going to be of length 4. It's going to start with my first current, which is 10 amps. In the very first part of my sequence, what it's going to do is it's actually going to do something called a temperature control. So as I set my target to 25, I want it to stabilize first before I begin measurements. And what that's going to do is I want to collect 5 good temperature readings between a range of 0.5 within the target range. So since I set to 25, I want 5 good readings within this range, which is 24.95 and 25.05. Once I have 5 good readings, I can move on. I can pause my script to make physical adjustments to my setup with a beep. So I'm going to have a sound notification when I'm done. And then I'm going to turn on my Keithley and measure current and data points the same way that I did in my previous sequence. But this time I'm also going to measure time as well. As it measures, it's going to collect the data and graph it in a similar way and export the data as well. I'll now press play on my sequence. The first thing it'll do, it'll set the temperature maximum to 30 and the laser current limit to 30 amps. This is for safety reasons. It will then set my laser temperature target to 25 degrees and my laser current target to 10 amps for my first loop. It'll then turn on the laser and begin making temperature readings. What I want is 5 stable readings to know that my laser has cooled down to a point where I can make more accurate readings on my source meter. It will take a couple of minutes for the first temperature check to stabilize, therefore I will fast forward the sequence. After about 2 to 3 minutes, a beep will notify me that the temperature has stabilized and the sequence will pause until there is a user input. The purpose of this pause and beep is to notify me to make a physical change on the setup by moving away the beam blocker to allow laser to shine onto the PPC chip. The second beep notifies me that the data is done collecting and it will now be graphed. Moving on, my sequence will increase the amplitude by 2 from 10 to 12 and it will continue on. It shouldn't take too long to get 5 stable readings as the amplitude increase is not that great and the temperature doesn't fluctuate too much. Once again, it'll give me a double beep pause to notify me when to make my physical change. It'll collect the data from the source meter and then it'll plot the data and save it into a file. The same will hold true for 14 amps, and finally for 16 amps. And finally, to wrap things up, this is the exported file that I've been mentioning so many times. It exports the data that I wanted, as the date, time, scan type, etc. 5 calculated parameters, such as the short circuit current, the open circuit voltage, the maximum power, the current at maximum power point, the voltage at maximum power point, and the fill factor. And then, of course, it exports all the voltage and current data as a tab delimited SCSV that you can load at any time. Thank you.
Okay, so thanks for that, Alex. And then now we're gonna move into the last part here to mention that Alex and Megan did develop different files, which is like measuring the dark current for fixed current, fixed voltage, turning off the laser script, and different LI like IV curves for 1 junction, 2 junction, 10 junctions, and using 2 lasers like 1310, as Megan was mentioning, for testing the 1310 and 1550 at the same time. So all of these scripts are available like for building on them if needs be. Okay, so these can be used, and also you can use them and edit them to do any other functionality you are interested in. Okay, so here at the end of this webinar, what I'm trying to say is some messages conveyed to our listeners today. First is OptiInstrument software can communicate with any instrument, which supports KB commands or Python serial commands. And the other thing is the beauty of OptiInstrument software is you can talk with a single GUI with all these different equipment from different vendors and use a single script to automate and control this equipment to run your tests. So the thing is right now, if you are interested in using OptiInstrument and you need support, or you need even to write the scripts and help you in automating your equipment, please contact us, and we can do that. Just to summarize what has the webinar delivered today is we discussed the design of photonic power converter chip given by our collaborator from Fraunhofer Institute, Dr. Henning Helmer. And then we showed the description of the setup by Dr. Megan Betty from University of Ottawa. And then we showed you the scripts running in OptiInstrument software developed by Alex and Megan. And then the demonstration here is shown, and for two types of measurements, one for dark current and one for IV curve. Now we are open for questions, and we can maybe go on, all of us. I'm going to stop sharing here and start taking the questions. So, okay, so there is a question here. How is the laser power relate to the power measured at the PV cell analytically? Maybe Henning, if you could elaborate on it, or Megan.
Sorry, can you repeat the question?
So the question says here, how is the laser power related to the power measured at the PV cell analytically? So it looked like, is there any analytical relationship between what you measure and what you apply in terms of laser power, maybe? I think it's the conversion efficiency is one parameter into it, and if you could.
Well, yeah, okay, right. So exactly. I mean, the analytic equation is that basically is as simple as that. That's a definition of the conversion efficiency. So if you kind of take the ratio of the input power of the light optical input power onto the cell surface times the conversion efficiency is the electrical output power. That is the definition of the efficiency. And as Megan pointed out, one thing to have in mind is, so for photovoltaics people, that's kind of natural to assume, but in principle it's not. Of course, the operating point of the device is quite important. So what Megan said is that you want to go to the maximum power point. That's kind of this knee of the typical IV curve is like this diode characteristic, which is shifted up by the light current. And you want to go into that knee, like the most rectangular you can be. That's the maximum power point where you can extract the maximum power. But of course, you can operate the cell at a different operating point depending on the system. So what voltage kind of you matches your the downstream system. And that is important to do to kind of optimize for performance of the system.
So it's very similar to the solar cells. Basically, you need to operate the cell at the maximum output power, basically, from the IV curve. Yeah, perfect. Thanks, Henning. Okay, another question here is how flexible is to format the output data file of the collected data? I think, Alex, if you could answer this, please.
Yeah, like everyone. So by default, we do have a post-processing button on the like on the UI, and with the post-processing, you can export any of the collected data from the machines to text or CSV. But as I showed in the video, you can also write your own custom functions that can export it to your own custom CSV or SCSV files. You just have to write a quick maybe 10-20 line function. But by default, we do have export to text, export to JSON, and export to CSV. But it is fairly flexible to make your own.
Okay, thanks, Alex. Another question, I think here, please provide a block schematic of the whole thing. So I would assume the whole thing is the setup, maybe from Megan, what you showed. Maybe that's a block diagram is already there, right? You showed. Maybe you can show it again or share it again, maybe.
Yeah,
that's
sorry, I'm just grabbing the.
So I think is that, yeah, maybe that should show. Yeah. You can speak about it.
This is a kind of a cartoon of the system, but it shows the major components. What it doesn't actually show here is it shows the optical path, so the optical fiber reflecting off the mirror down to the sample. What it doesn't show is the electrical connection. So you can see in the picture here that we have these probes that make electrical connection to the sample itself. And through the back, it's conducted through this temperature controlled conductive stage. So yeah. Actually,
there is another question here about the packaging of this. This is the chip on carrier, right? Right now it's not packaged.
Yeah, so this is a bare cell. This is not mounted on carrier. You could certainly measure chip on carrier using this system as well.
Okay, so maybe Henning, if you could elaborate on the packaging of these chips.
Sure. I mean, maybe just to add to what Megan just said before, what is important for these, like to do like precise measurements, is to go for 4-point probe measurements, so that you have basically one probe for current and one for voltage on both terminals, so that you have four kind of contacts to the chip as close as possible, so that you don't deteriorate or your precision by voltage drop across the wire. That's important to have in mind. And for packaging, yeah, I mean, so what we do is like the chip fabrication, of course, is on wafer level first of all, and then like what you've just seen is a piece of a wafer that we ship to Canada to make these measurements, which is of course the most straightforward way to do. So you don't need to do any packaging. But of course, for like more a commercial product, for example, of course you would do that, and that's roughly similar, I would say, to what is done in laser packaging. Of course, the chip is much larger than a typical laser chip is, but in principle, it's similar. It's just the opposite. So it's a very similar device. The light goes the other direction. So now it's not like you put in power, electrical power, and light is leaving the package, but it's just the opposite. But in principle, it's the same. You need to, if you want to seal it, you put the like transistor outline TO housing is a typical package that is used, for example, and you put a cap on and you have a window layer that should be transparent, of course, highly transparent for the laser light. Otherwise, that's like an obvious loss channel that you want to avoid. And you do like wire bonding for the front contacting, and typically solder or like conductive gluing of the backside onto the housing. But you can also go for planar like chip on carrier, or I mean any other microelectronics packaging that you want, basically, that matches your system requirements. So there's no one way to do that.
Thanks. There's a question here about the beam. Actually, it says that during the measurements, did you verify that the beam is not affected by the beam attenuation? I'm worried about thermal effect in the filter. This may change the beam's shape or size on the photonic power converter chip. So, any comment on it, please?
Yeah, sure. So that's actually an interesting question. And the short answer is that we have noticed some small effects as the attenuator does heat up. That does tend to stabilize. So once that temperature is stable, then we can do a measurement at that point, and we're not noticing a shift. Yeah, it is a factor, and it's something that we need to consider in terms of what powers we're subjecting or we're impinging on that filter. So the higher the power, the more thermal effects we're going to have. So it's a consideration, and it's something that we're working out, but it doesn't seem to be a massive effect.
Maybe I would like to add something on that. So I'm not sure who's in the audience today, but something that is definitely not the case is that in this field of power by light or photonic power converter developments and respective measurements, which we discussed today, there is no standard. So there's no industry standard today. There is a standard for concentrated solar cells, which is also not around for very long, which are very similar devices, also from size and in terms of like current and voltages that you generate. It's similar metrics. Of course, it's also photovoltaic cells. But like there is no standard for photonic power converters, and I think it's lacking because there's, I mean, even industries today that sell these chips as products on the market, but there is no like agreement among the community how you make a calibrated measurement and what even calibrated means. And of course, I mean, as Megan just said, I think the question aims in that direction, is how do you actually determine the laser power? So you measure very accurately an electrical output, but if you don't know the input, what is the efficiency then, or what is the uncertainty of this efficiency? And there's numbers around that, let's say, can be questioned, of course, all of them, also our own measurements. And I think one thing that we have been discussing also in this consortium of the project, University of Ottawa, Fraunhofer ISE, and other parties, is what steps need to be taken towards a standard. And I invite everyone like who is maybe in the audience today, who is somehow involved in system applications, manufacturing of those devices, to reach out to me or to Megan or to Ahmad, I guess, as well. If you have contact there, to join this discussion, to see what is actually the requirements from the market side, from research, engineering, to make steps towards such a thing as a standardization for photonic power converters.
Okay. The question actually here, Henning, is just to add up, I mean, is the wavelength bands, because originally the wavelength band originally was at 850 or 900, and then now at 1310 and 1550. Is the standards is different, or still the same applies for every wavelength band?
No, well, yeah. There is different wavelength bands, and I think they will remain. there's good reasons for some applications to be in the 835, 800, whatever, like a roundish range of application for laser availability, for example, or cost, of course, is an issue. There will be applications in the 1300 or 1500 nanometer band. So this is, I think, something that will be there. So we need to, as a community, from the characterization point of view, we need to come up with a procedure or like some means to make sure that we are able to give, let's say, a calibrated value of efficiency that is meaningful. And this discussion is still needed. So, I mean, in principle, now you could say, okay, the solution is we just have one institute or a couple of institutes in the world that have an unlimited number of laser sources available, and they're all calibrated in terms of power level and whatnot. And you can do all these kinds of measurements under all kinds of different operating conditions, but I think that's not really viable or pragmatic. That won't happen. So we need to have an understanding. And then in the end, it's a question of what is the, like, let's say, minimum amount of agreement that we need to have trustworthy data that we can exchange and live with. And I think it will always stay a matter of fact that in real applications, you have things like temperature changing, so that may affect the laser wavelengths, because of course the laser has a drift if it heats up and so on. So this is things that will take place. And then it's a different thing whether you have like some in photovoltaics, you give something like standard testing conditions. It's like a rated efficiency. That's the one you give on a certificate of a technical data sheet. And that's, for example, 25 degrees C of the solar cell. In operation on your rooftop, the cells in sun and summer have a much higher temperature. And these things will be the same for PPCs, I think. But the agreement is still not there. What is the actual standard operating conditions for those devices?
Thank you. Another question here comes is, what is the maximum number of instruments we can integrate? So, I mean, there is no limitation to in terms of OptiInstrument. So the OptiInstrument, as long as you can communicate with the equipment, you can write the scripts which controls it, and then that's it. That's what we need in principle. So there is no limit, physical limit in the software operation and control of these instruments. Okay, so a question here is about, does the efficiency have to do with the channel, like when you transmit it through optical wireless channel? So like, I think it means here, if it is a free space or fiber, does the efficiency would be different? I'm not sure if maybe Henning, you could comment on it, or Megan. Is the efficiency, I think conversion efficiency, they mean here.
So free space versus fiber.
Exactly, I think so, yeah.
So your efficiency is going to depend on what wavelength of light you have when it arrives at the cell. It's going to depend on what the profile of that light is, the incident profile, and the temperature. Those would be the primary factors that are going to impact the efficiency. So that there might be some changes. For example, if you start with the same wavelength at the beginning of the fiber, or the same profile, that profile might change as it travels through the fiber. You might have some impact on your I mean, when you're monochromatic, you're not going to get a significant impact on spectrum, but your intensity is going to change as you travel through different media. But ultimately, it's not so much dependent on the channel as it is dependent on what the beam looks like when it arrives at the cell, if that makes sense.
Okay, thanks. Then, is there a reason why you tested 1310 and 1550 at the same time on the chip? Like, why you did that? Is there any physical reason for that, or?
Yeah, I can take that. So maybe just to add on what Megan just said. The channel, I mean, in the end, that's like one part of this, in which system or which application you want to have what components depends on, of course, where's the losses and what is the cost of the components. And there is some kind of a trade-off it's a multi-parameter space for optimization. So there's no easy answer to that, but that's in the end what you need to consider. Availability, cost, performance, losses. And in terms to your last question now about the different wavelengths, that's a simple answer. for this power by light application, you don't want to do that with 2 different wavelengths at a time. That's not the application. This is for like scientific understanding of the performance of these complex structures, which consist of several stacked cells, as I showed, these multi-junction cells. So one way of probing how they interconnect electrically and optically, there's actually an interplay between these different subcells. So we give, with the 1300 nanometer, we can give the top cell more light, so it can vary kind of the illumination condition in these individual junctions in the stack to understand in more depth the influence on performance on these devices.
Perfect, thank you. Thanks very much. It's 11 o'clock. Do you want to take more questions, or we need to conclude? Depends on your time. I guess you are in Germany. You are late evening right now for you, right? So what do you think?
Well, maybe I just read that there's one more question. I think that is maximum end-to-end conversion efficiency. E to E, I think, is end-to-end conversion, I guess, or electrical to electrical. So maybe just a quick answer on that one. Yes, it does depend on wavelengths, but again, that's a matter of what is the, the main components is the conversion efficiency, electrical to optical of the laser first. Then it's a transmission, and I would say in the very first approximation, even I would say the transmission is no loss at all, which of course in reality is absolutely not true, but that would be my first pick. And then you have the PV cell, which does the conversion of optical back to electrical, which is an efficiency. And let's say very rough numbers for rule of thumb estimations is laser is 50% and the PPC is 50%, meaning your overall efficiency is 25. And in real systems, it will be lower, but I think that's a number that is good to take home for today. And if you have an application where you find that you can live with that, or that a loss of that magnitude is still a win for the application, so in replacing a copper cable, for example, then it's a good one. And if it's not, it's not. So I think that's important to understand, but I'm convinced, absolutely convinced, that there is so much room in the future for new applications to come up that I think this is something you can all take home and brainstorm what possible future applications for this technology will be.
Thanks very much, Henning, and thanks Megan, thanks Alex, and thanks to everyone attending the webinar. I think there would be a recording and passed to everyone attending and who didn't attend but did register. All the questions remaining we're gonna contact through emails, and if you have any questions still, please contact us. You can send the emails to my email address here or to support@Optiwave, and then we try to help you. As I mentioned, we are open to collaborate with any user who wants to make his script to automate the equipment and to do any kind of testing for photonic integrated circuits or for any other application. Thank you very much for everyone, and have a good day. Bye-bye.
Yeah, thanks so much for hosting.
Thank you. Thanks, Megan. Thanks, Alex. Bye-bye.